Year 13, Chapter 10, Integration, Lesson 4, Integrating Exponential Functions. So we're going to start by remembering that integration can be thought of as the reverse of differentiation. And we know how to differentiate e to the power x. We know that d by dx of e to the x is e to the power x. So if we start with e to the x and we differentiate it, we get e to the x. So this means if we integrate e to the x, we must also get e to the x. And this leads us to the result that the integral of e to the x with respect to x is equal to e to the x, and of course plus a constant of integration. So let's have a look at how we can integrate using integration by substitution when we're dealing with exponential functions. We have an example here. It's a composite function that's being integrated. You can see the e to the 5x plus 1 and the inner function here 5x plus 1. I'm going to start by using the full integration by substitution process. So u equals 5x plus 1, du by dx equals 5, and then we have our sort of pretend rearrangement. Remember, this is just a step of convenience, which allows us to get to the answer in a simplified way. So this gives me the integral of e to the u, and in place of dx, I have this. Now, I can pull out a factor of 1/5, so I have 1/5 the integral of e to the u du. Now, I know that an exponential function will differentiate to another exponential function like that, and I can now carry out this integral. So I get 1/5 e to the u plus a constant of integration. And of course I want to replace u with what it is in terms of x, so my final answer, 1/5 e to the 5x plus 1 plus constant. So look at the original integral, e to the 5x plus 1, and then look at the answer and think about how you could get there by inspection, which would mean that you wouldn't have to write out the full integration by substitution process. Can you see the connection? Think about that whilst we do a few more examples. So we're going to do this example again using the full process of integration by substitution. Notice there's a factor here of 3, which is just a multiplicative constant. We have our inner function here, u, which is 2 minus 4x. Differentiate this with respect to x, du by dx is negative 4, and then our pretend sort of rearrangement, we have this result here. So we're ready to perform the substitution. So the 3 I'm going to pull outside of the integral for simplicity. Then I have e to the power of u, and of course I'm going to replace dx by this. And I can pull out that constant of negative 1/4 out of the integral as well. So I then have a very, very simple integral to perform. So the answer in terms of u is negative 3/4 e to the u plus a constant. But of course we're going to replace u with 2 minus 4x. So our answer is negative 3/4 e to the 2 minus 4x plus a constant of integration. So again, consider the question, the original integral, and consider the answer. So we know that exponential functions integrate to exponential functions. The 3 was just a multiplicative factor, but of course, can you see we've divided by the derivative of the inner function? So it's that same concept being applied again. And of course, it only works because this inner function here is linear. So what about this next question? the integral of 2 over e to the 6x with respect to x. So I'm going to rewrite this first of all. I'll pull this factor of 2 outside of my integral, and then I'm going to rewrite 1 over e to the 6x as e to the negative 6x. And then u is equal to negative 6x, du by dx is negative 6, and then here is my little convenient step which allows me to perform the integration very simply. So I then have 2, the integral of e to the u, and in place of this we have this. So I can now pull any multiplicative constants out to the front. 2 over negative 6 is the same as negative a third. And then I have the integral of u with respect to u, which then gives me negative a third e to the u plus a constant of integration. And of course, final step, let's replace u with negative 6x. So we have negative 1/3 e to the negative 6x plus a constant of integration. And again, look at the original integral and the final answer. You can see that in both we feature e to the negative 6x, but in the answer we have divided by the derivative of this inner function, which gives us the negative a third. And of course this only worked again as a step of inspection. We were only really able to do this by inspection because this inner function is linear. So we can generalise this very easily if we are carrying out the integral of k e to the power of ax plus b with respect to x, then this is going to equal k over a e to the ax plus b plus a constant of integration. So we know that exponential functions integrate to exponential functions, and of course we need to make sure we divide by the derivative of the inner function. Now, as we've said previously, if we're going to do this by inspection, which is essentially what this generalisation is, this must be linear. Now, we can prove this quite neatly by using full integration by substitution. If you allow u to equal ax plus b, then du by dx is equal to a, and then here's the sort of faux rearrangement step that we use for convenience. And our integral then becomes the integral of k, which can come outside of the integral sign, e to the power of u, and we have to make sure we use this as well. So pulling k over a outside, we then have the integral of u with respect to u, which of course gives us k over a e to the u, which we can express as k over a e to the power of ax plus b, plus our constant of integration, which of course is the same result that we get by inspection. So if you have a very simple exponential function and the power is a linear expression, then we can simply use expression to carry out the integration very, very simply. Now let's look at some slightly harder examples which we can't do as easily. Now here we have a product, and notice that this inner function here, u, which is 2x squared plus 3, when we differentiate this, we get a result which is a multiple of this x over here. So we can see where this is going. We've been here before. We've done this with previous examples. This is going to be one of those examples where we use integration by substitution and there is a very convenient cancellation. So let's continue with our rearrangement. And it's this x in the denominator here that's going to help us with this x over here. So, as always, I like to leave this term here as it is until we see the cancellation. We then have e to the power of u, and then in place of dx, I've got this. So, watch the cancellation take place, and we're left with a quarter outside the integral sign, the integral of e to the u du. So that is, of course, a quarter of e to the u plus c. And remember, u is, of course, the same as 2x squared plus 3. So we get a quarter e to the 2x squared plus 3 plus a constant. Let's look at another example. This time we're going to do a definite integral. And we're also going to include some trigonometric functions. Have a look at this. Now, look at this function here, u equals cos x. We know that the derivative of u with respect to x is negative sine x, which is going to help with this sine x here in the integral. So, here's my faux rearrangement. There we go. And don't forget, we have limits here, so we're going to need to convert from limits which are in terms of x to limits which are in terms of u. And we do that, again, via this substitution that we've set up here. U equals the cosine of x. So, if x is equal to pi by 6, what does u equal? U equals the cosine of pi by 6, which is root 3 over 2. If x is equal to 2 pi by 3, which is the upper limit, u is the cosine of this, which is negative a half. So this is going to be interesting because you will notice that when we set up the integral in a second, the new upper limit in terms of u will be lower than the lower limit. So here we go. We have the integral of, now, as always, I'm going to leave this part here until we see the cancellation, so sine x. E to the cos x becomes e to the u, and then in place of dx, I want this. Now, watch the cancellation. And I'm also going to put in my limits as well. So if you remember, my lower limit is root 3 over 2, and my upper limit is negative a half. Now, we've been here before, and we've seen what we can do. If we want to swap the limits around, so this becomes root 3 over 2, and this becomes negative a half, then we need a negative in front of the integral, like that. So what else do we then have left? We have e to the u, we have another negative, which is here, like that. So overall, the integral simply becomes the integral of e to the u with respect to u between these two limits. So integrating, we get e to the u. We don't need a constant because this is a definite integral, and all we then need to do is substitute in the limits and subtract. Now remember, because the integral is in terms of u and the limits are in terms of u, we don't need to put this back in terms of x. From this point onwards, we carry on the whole integral in terms of u. Everything, including the limits, has been converted to u, the variable u.